Hello, everyone. Our topic is about water filtration and superhydrophobicity. And our project is to use wettability properties to filter pesticides from water. And I'm Han Yi.
I'm James. I'm John.
I'm Sarah.
I'm Lauren.
Okay, and today we may focus on one pesticide, and that is known as Roundup. It is a very common pesticide, and the active ingredient in the Roundup is glyphosate isopropyl salt. And about the Roundup, there is a controversy whether it will lead to cancer to humans. And of course, the company which produces Roundup will not see it is risky, but actually, according to many science organizations, it may lead to the cancer. And it may not lead to cancer, others may think. As for animals, it is slightly toxic. As we can see, here is a structure of the glyphosate. We can see it has 3 OH groups, 1 NH group, which make it polar and hydrophilic. 3 OH groups also make it acidic. It is nature that is the most acidic part may donate 1 proton to the most basic part. So glyphosate may look like this. But in the Roundup, actually, it's glyphosate isopropyl salt look like this. And according to these, glyphosate is corrosive, and also it may be harmful to the environment. Water filtration, we use activated carbon, and the carbon is processed to have low volume pools, and it is available for adsorption. The glyphosate itself is small and it can easily pass through the filter, but with activated carbon, we can filter it. It's already proven that activated carbon can filter glyphosate. That's why we use activated carbon.
So here's a brief explanation of the wettability properties. So wettability basically means the measure the things the water adheres to a solid surface. So it has 4 properties: superhydrophilic, hydrophilic, hydrophobic, and superhydrophobic. What hydrophilic basically means water loving, which is water can dissolve in water, and hydrophobic means repels to water. And we usually use the contact angle between the liquids and the solid to measure the hydrophobicity of the liquid. If it is less than 90 degrees, it will be hydrophilic, and if it's greater than 90 degrees, it will be hydrophobic. So our guiding question is that what is the most effective way to filter pesticides out of water? So in our case, we use hydrophilic filter and hydrophobic filter. And we hypothesize that the hydrophilic filter with nanoparticles will remove more glyphosate than the hydrophobic filter, because water will pass through the filter, and the activated carbon would prevent the glyphosates from passing through the filter. And it is significant because you'll remove the glyphosate from the water, and it'll reduce toxicity in the water streams and prevent further pollution to the ocean. So we use 2 solutions in our experiment. The first one, we include 16.7% of Roundup, which is our pesticide. This means that we use 5 milliliters of Roundup plus 25 milliliters of water in our first solution. And the second solutions, we include 66% of Roundup, which means we have 20 milliliters of Roundup and 10 milliliters of water.
As
first step for our experiment was actually synthesizing the nylon that we're going to use for our 4 different filters. And to do this, we took our hexamethylene-diamine in an NaOH solution and Z-balkyl chloride in a hexane solution. And so we slowly mixed the two, and we formed this, as you can see here, with the 2 distinct layers. And at the intersection right here, the nylon was actually formed. And then from there, we used the glass stirring rod to swirl the nylon into strands, and then we put it in a jar, as you can see here. We did this 4 different times for our 4 different filters that we created. And then we also had to synthesize our silver nanoparticles, which we used to create the nano roughness of our superhydrophobic and superhydrophilic filters. So we heated a water bath to 80 degrees Celsius. Then we combined our 25 milliliters of silver nitrate with 25 milliliters of sodium citrate. And then we heated it using the water bath and stirred it with a magnetic stir bar. And we waited for the solution to turn a light yellow color, which meant that the silver nanoparticles had formed in the solution. And then we also had to functionalize our nylon to give it the wettability properties that we desired for our 4 different filters. So the first filter we made was our hydrophilic one, which was just made from regular nylon, because nylon is naturally polar, which makes it hydrophilic. And then we made a hydrophobic filter by adding iodoxantane to it, which made it nonpolar and hydrophobic. And then we made a superhydrophobic one by using octanthiol as our nonpolar group, and then we added silver nanoparticles, which provided the nano roughness that aided this make it super hydrophobic. And then we made a super hydrophilic one by taking regular nylon and adding silver nanoparticles.
So these are 2 filters that we made in our glass pipette. So for the hydrophobic filter, it was cotton to keep the nylon filter in place, and we functionalized the nylon with iodoxantane to make it nonpolar, making it hydrophobic. And for the hydrophilic filter, it was just cotton with nylon, and because nylon is hydrophilic, we didn't have to do anything else to it. For the superhydrophobic filter, it was the cotton, and then we functionalized nylon with the 1-octanethiol, and we soaked it in silver nanoparticles to give it the superhydrophobic. And for the superhydrophilic filter, we did nylon and soaked it in silver nanoparticles to increase the surface area to make it superhydrophilic. So for our filtration system, we added activated carbon into our solution, and what activated carbon does is that it attaches itself to glyphosate, and this prevents glyphosate from filtering through with the non-acidic solution that comes out. And we tested these filters by suspending our pipette filter over the jar and putting our solution and pushing air through it so the yield would come out.
So this is the data that we collected from our experiment, and we measured pH because the pH of pure Roundup is acidic, which is 4.58. We originally planned to do 4 different concentrations, but with the limited time and the long process it took to filter the concentrations, we only did the 2 extremes, 16% concentration Roundup and 66% concentration Roundup. And the pH for the 16% was 4.81 and the 66% was 4.62. And after filtering it through the 4 different filters, we got the numbers in the middle pH column. And the last column shows the change in the pH from before and after the filtration. And we can see here that the hydrophilic filter was consistently the most efficient for both concentrations. So we came to a conclusion that the hydrophilic filter, the filtered solution for the hydrophilic filter was closest to neutral pH, which is 7. And it filtered out the most Roundup, which shows that our hypothesis was only partially correct because we hypothesized that the hydrophilic filter with nanoparticles would be the most efficient. And from this bar graph of the pH of resulting solutions, we can see that there's a pattern. So the hydrophilic was consistently the most efficient for both concentrations. So some possible errors that we might have had is pH measurements. Because it took such a long time to filter out the solutions, we only had a small sample size and we're not able to use the pH meter. So we used the pH paper, which might not be as effective And also when we used the pH meter for one of the solutions, we saw that the numbers we got were kind of different, so that could have been a possible error. Also, we could have incorrect functionalization, but we would not know because we did not test the wettability of the filters. So some future directions could be having more time to filter more solutions so we could use the pH meter, and using all the different concentrations instead of the two extremes, and also measuring the contact angle of the filters to see if they have the correct wettability that we desire. Thank you. Any questions?
Thank you. That was an excellent presentation. Did you look ahead to see how you might use this for filtering large amounts of water, like groundwater, where pesticides and pollutants are a significant environmental problem?
So yes, that is the major application of what we were studying. So currently it's proven that activated carbon does help with the filtration process of glyphosate along with different other pesticides. But we were testing to see if there was a more efficient filter design that we could use. Wettability properties just make the process more efficient and effective.
Any other questions?
So did you time how fast the different filters went?
We were going to, but then we thought that would be too many variables. But we saw that the hydrophilic was the fastest. We got through both of the concentrations before the other filters got through the first concentration.
And so how do you interpret that? In terms of the earlier question about actually using this for real groundwater remediation, how is that result important?
Well, the hydrophilic filter, as you can see, was the most efficient. It got most of the Roundup out, and it was also the fastest. It was the fastest time for getting rid of the Roundup, and also it was closest to neutral pH. So if we were to filter out a larger amount of Roundup in the real world, then we would use the hydrophilic filter.
Yeah, there are lots of good filters that work, but most of them are just way too slow for real water treatment. So speed is a super important variable. Okay, good.